So the last video was called Applications of Newton's Laws, but really it should have been called The First Examples of Applications of Newton's Laws. And we covered ramps and normal force changing on ramps and elevators and tension, and now we're going to do some more things. Specifically, we're going to talk about multiple objects connected with ropes or touching each other. So we're going to have 3 boxes on a table on a frictionless table. So we have a 2 kg box connected by rope we're going to call A, to a little 1 kg box connected by rope we're going to call B, to a big 3 kg box, and we're going to pull on the right side of the 3 kg box. I guess there's a little handle there, with a force of 12 newtons. So the main question I want to answer here is, what is the acceleration? So there are a couple of different ways to do that. One is a really long and tedious way, and then there's a short way. So if we do free body diagrams, and I'm going to go ahead and make boxes because they're all box shaped and I'm going to label them. So the 2 kg object, there is of course a force of gravity and there's normal force. They cancel out. And then there's a tension from rope A. So FTA. There's no friction, so that's it. Then we have the 1 kg box and there's a normal force on it. Wait, now I have 2 normal forces. This is for the 2 kg object. This is on the 1 kg object. And of course it has gravity. But now this is the 1 kg object, and this is the 2 kg object. Now it has 2 ropes attached to it. FTA is attached on this side, so it's holding it back. FTB is pulling it forward. And then finally we have the 3 kg box. So we have a third force of gravity. We have a third normal force. And there are 2 forces on the 3 kg. The rope is pulling it back, but notice I don't put A on it because rope A is not touching the 3 kilogram object. And then the 12 newtons is applied directly to the 3 kilograms. So this is the person, and it's equal to 12 newtons. Now, I have a lot of, how do I deal with all of this? But I want you to, instead of looking little tiny, I want you to look big picture. So if we go big picture, I know this normal and force of gravity cancel out. We're on a horizontal surface, nothing's going on vertically, so this better be equal to this or something bad's going to happen. If gravity was bigger, the table would break. If the normal force was bigger, it'd fly off in the air. So this and this cancel. For the same reason, this and this cancel. And for the same reason, this and this cancel. So now I have these ropes, and then this person. Well, if I go big picture, these 2 forces are from this rope that connects these 2 objects. This is not that different than talking about, say, my hand. I could talk separately about this part of my hand and this part of my hand, but they're connected by muscles in a joint. And so I can think of them as one object. Or we have 3 objects here. My finger's a good example. I have 3 sections, and it's all connected. So I can think about each part individually, or you can think about it as one thing. And if I'm thinking about my whole finger, I do not care about this little muscle tendon, whatever it is, and I don't care about this little muscle tendon, whatever it is. I just care about the overall effect that lets me tap my whole finger. So these forces exist, but they're inside the system. In fact, these are a third law pair, because this is the force on the 2 kg object from the 1 kg object, and this is the force on the 1 kg object from the 2 kg object. So it's a third law pair. We've got the same thing with this rope. It's a third law pair, 3 pulling on 1, 1 pulling on 3. So if we go outside the system, outside the system. Internal, so we don't care. Canceled out, yeah, they're both external to the system, but canceled out, canceled out, canceled out. All that's left is the force exerted by the person. So, in order to find the acceleration, use the big picture. This is some phrasing I got from actually somebody else's video that I really liked. Use the big picture. You know acceleration is net force divided by mass. This is net external force, and this is total mass. So for this problem, everything either cancels or is an inside, and we're left with 12 newtons. And to get the total mass, mass is a scalar. You just add it up. 2 plus 1 plus 3 is 6 kilograms. This whole thing accelerates to the right at 2 meters per second squared. Now let's say I want to find these tensions. When we're doing tension, and make sure everything stays on the screen, tension, we need to use tunnel vision. So if I want to find FTA, I can either do a calculation on this box or on this box, because FTA is on both of them. Well, on this box, I know normal and gravity cancel out. The only force that's left on just this box is FTA. That must cause this acceleration directly. So just the 2 kg box, if I redraw its free body diagram, F norm, FG, FTA, you know these cancel, so all that's left for the net force must be FTA. And that, of course, has to produce mass times acceleration. So for this problem, FTA would be mass of the 2 kg block. This is one of the places when you focus in, make sure you remember which object you're working with. We're doing the 2 kg box, so this is just 2 kilograms times the 2 meters per second squared. So rope A has a tension of 4 newtons. Now, to get rope B, 2 different ways to do it. One, we can do the same big picture idea on just the second 2 boxes. So if I look at just these 2 boxes, cancels out, internal, FTB is external. So big picture of the blue box, which is 2 kg in the 1 kg objects. Net force equals mass times acceleration. The net force is caused by just FTB. But the mass that's being accelerated is both of these objects, 2 plus 1 kilograms. And we already know the acceleration. It's 2 meters per second squared. So FTB must be equal to 6 newtons. So, yes, it's all on the screen. It's almost all on the screen. If we slide back down to this, the 12 Newton force ends up pulling all the mass. Rope B pulls everything behind it. Rope A pulls only the one thing behind it. And that's how we get these different forces. In the lab, you did an Atwood machine, 2 objects hanging over a pulley. For our next multiple object system, we are going to look at what is called a modified Atwood machine. It's named an Atwood machine, by the way, after the man who invented it, an Atwood machine, and his purpose was actually to do this to get a really good calculation for the acceleration due to gravity, which we now know really well, 9.8. But he did this purely with stopwatches, or no, this was even before stopwatches. He probably used like a water clock or something. And so he needed a system that he could slow down and then from that extract the acceleration due to gravity. So he did what you did in the lab, but with very small mass differences, so he could get a very, very accurate timing with very, very simple technology. I mean, even you using a stopwatch would be an advancement on what he did, and he got very good results. So a modified Atwood machine, we have a frictionless table. Don't worry, we'll do friction eventually. Frictionless table, and we have object M1. And then there's a pulley on the end of the table, and there's a string over it, and attached to the other end of the string is a second object, M2. And it is freely hanging in space. So instead of in the lab, one thing going down while the other one up, this one goes down, this one goes to the right. So if we look at all the forces again, so this is M1, we have normal, force of gravity, and I'm going to call it gravity 1, because of course we're going to end up one with a second object. And then we have a tension in the rope. FT, I'll move a label here, M1. On object 2, we have its force of gravity, and we have the same tension, because it's the same rope. The rope changes direction over the pulley, but the amount of force it exerts does not change. Now we know M2 is going to go down. That's why I drew FT a little bit smaller here. And I don't think I did a good job, but this FT and this FT should be the same. So now if we're looking for the acceleration, we need net external force divided by total mass. So big picture, we know normal and FG1 cancel. We know FT is internal, it's a third law pair. This tension exists because M2 is pulling on the rope that's attached to M1. This tension exists because M1 is pulling on the rope holding back M2. So these are a third law pair together. They are internal to the system. All that's left over is FG2. So you know the force of gravity is mass times gravity, so M2 times G divided by the total mass, which G just added up. Now for the tension. For tension, we do tunnel vision. In this problem, the only force that matters for calculating acceleration is the tension on M1, because the normal force and the force of gravity on object 1 cancel out. So you can calculate the tension either way. We're actually going to do it both ways because I want to prove to you that it's the same. But we'll start with the easier one. This tension is the only thing that produces the acceleration of this. It's not canceled out partially by friction or a spring or another person over here or anything like that. So Ft equals the net force on object 1, which means it's the mass of object 1 times the acceleration. Remember, the acceleration has to be the same for the two objects. Actually, I don't think I said this. It has to be the same because if it wasn't, like let's say M2 accelerated faster than M1, the string would break. If M2 didn't accelerate as fast as M1, the string would bunch up. Neither of those is observed. The string stays taut the whole way. They have the same acceleration. Another way of saying that, remember, acceleration is change in velocity and velocity is change in position. For every couple of centimeters this falls down, this moves over. So for every couple of centimeters it falls down faster and faster, this is going to move over faster and faster. So now let's do a little algebra. If the tension is mass 1 times the acceleration, this is the acceleration. So this is M1 times M2 times G all over the sum of the masses. Don't worry, in Schoology you get to do numbers. Well, now I want to do the same thing again, but with the second object. So on object 2, we have two different forces. If we only look at object 2, force of gravity must be greater than the tension because this accelerates downward, that's observed. So our net force is force of gravity 2 minus the tension. So if I start from net force equals mass times acceleration, this is object 2. So the net force is Fg2 minus Ft equals M2A. So doing some algebra, add this over here, subtract this over here, and then change the order. You can deal with it. Ft equals Fg2 minus M2A. Again, I subtracted mass 2A over here, so Fg2 minus M2A, and then added Ft over here, and then I swapped the whole thing. So Fg2 is M2 times G minus M2A is back here, M2G over M1 plus M2. Okay, I'm sliding the book up. Yes, this is going to take a minute. You can handle it. So equals M2 times G minus, I need to multiply here. I'm not distributing, I'm multiplying. M2 squared G over M1 plus M2. I need a common denominator. Well, this is my only denominator, so I'm going to multiply both the top and bottom by the same thing. So this is M2G times M1 plus M2 all over M1 plus M2 minus M2 squared G over M1 plus M2. Now I need to distribute. So I have M1 and M2 times G, and then I have M2 times M2, so M2 squared times G. And then now that I have my common denominator, I can write it all over one big thing. So minus M2 squared G. Again, M2G times M1, so M1 M2G, M2G times M2, M2 squared G, and then minus M2 squared G. Well, that cancels. And we're left with M1 M2G over M1 plus M2. Well, we already knew that. It's right there. So when you have the option, pick the easier one. In this case, this one was much easier to do than this one, but we got the same answer. And that is an important thing to realize. We got the same answer. So, if we do a full Atwood machine, or just the word, Atwood machine, this is like in the lab. We have a pulley, we have M1, we have M2. Let's make M1 bigger than M2. So M1's going to accelerate down, M2 is going to accelerate up. M1, we have tension and gravity, and I'm going to make gravity 1 longer because this one accelerates down. On M2, it's the same amount of tension because it's the same string, but this has a lesser mass, and so it has a lesser force of gravity. Now, nothing cancels in this one. There's no normal force and gravity to cancel, but Ft is inside the system. We now have 2 external forces. And this is where this idea gets a little bit tricky. Be careful. Make sure you understand the logic of it. Don't do simple math. These 2 are in the same direction, vertically downward, but they're having opposite effects on the system. Fg1, the larger weight, is pulling down. It's making this go faster and faster. It's being held back by the weight of the lighter one. If this wasn't here, we'd get full 9.8 acceleration. So when we do acceleration is the net external force divided by the total mass, the external force is the difference in these 2 weights, Fg1 minus Fg2 over M1 plus M2. And then just a little bit of algebra here. Of course, this is M1G minus M2G over M1 plus M2. And finally, we're going to factor G. You don't have to factor G. In fact, if you were doing a calculation with number, you may or may not choose to. But this pulls out the fact that the acceleration depends on the difference in the masses, and then times the acceleration due to gravity. So of course it's the difference in the weights that's really causing this. This whole problem would not occur if we were not on some location with gravity, but it's the difference in the masses that produces the acceleration. So when Atwood built this, and he was trying to get a really, really good number for G, in order to measure A effectively, he needed something that took a really long time. And so he used a very small difference in masses. And that's our introduction. It's not the end of it, but that's our introduction to multiple objects.